Hello everyone, my name is Panya Thanwisai, a PhD student from Mechanical and Materials Engineering working with Professor Wang. Today I am going to present my research project entitled Metal Powder Production with Electrolysis. Alright, let's get started. I think we all know that iron is one of the most important metal that's been used in every construction of man. However, the conventional process of iron making, the carbothermic reduction generates a large amount of carbon dioxide gas into the environment, which is around 2 tons of carbon dioxide gas per ton of iron produced. This number accounts for around 5% of global carbon dioxide gas emission. You can see that this is kind of detrimental to our environment. So our main goal in this project is to decarbonize the conventional iron making by developing a more novel and more sustainable process to replace the conventional one. In addition to tackling the problem of carbon dioxide gas emission from the iron making, we also provide a better way to manage metal waste, for example, copper tailings and red mud, by utilizing them as a feedstock in the iron production, because those metal waste contain a high amount of iron oxide. So we can use it instead of dumping them into the landfill without any utilization. For our innovation, we proposed the low temperature electrolysis with the 3D iron oxide colloidal electrode to produce the iron powder sustainably at a low temperature of 100 Celsius degree. Actually, the 3D conductive electrode design is proposed to enable a fast and efficient electrochemical reduction by utilizing carbon additives acting as an electronic conductive network, and sodium hydroxide solution will act as the ionic conductive network. Based on the electrochemical reduction reactions shown here, we can see that the iron powders can be produced by the electrolysis of the colloidal electrode to form high purity iron powder with no any carbon dioxide gas emission. We would say that there is just only oxygen gas is produced as a byproduct. So for our methodology, we firstly form the iron oxide carbon colloidal electrode by mixing the carbon powder, iron oxide powders, and sodium hydroxide solution together to form a flowable slurry, and then we run the electrolysis. And after the reaction finish, we can obtain the iron high purity iron powders, and then we can separate the iron powders from carbon powders by utilizing a simple magnetic separation. And also I would like to note that we can also reuse the separated carbon powders and sodium hydroxide solution in other experiment, showing the closed loop process without any resource waste. So for the results shown here, the electrolysis current versus the reaction time shows that the 3D conductive colloidal electrode yield a higher electrolysis current, resulting in faster reaction time compared to the slurry with no carbon additives. And the X-ray diffraction show the high purity of produced iron powder more than 95%, contributing to more than 95% of electrolysis efficiency. These results indicate the effectiveness of the design of 3D conductive network colloidal electrode. And the SEM image show the morphology of the obtained iron powder. We can see that the 5 nano size iron powders with a spherical shape can be obtained, and again the magnetic separation is used to separate the carbon powders from the iron powder. According to the EDS mapping, the signal of carbon is decreased significantly after the separation, showing the effectiveness of magnetic separation. So in addition to the iron powders, this process can be applied to produce other metal or alloy powders, for example copper, silver, and even iron nickel alloy, showing the promising process to revolutionize the metal production. In addition to these elements, we can also use this method to produce like other possible like elements shown in the periodic table based on the thermodynamic analysis. To scale up the process, according to the flowability of the slurry, we can use the flow electrolysis design to allow continuous production and easy collection for further scale up process. Altogether, the low temperature electrolysis is highly efficient, less energy consumptive, is of like no direct carbon dioxide gas emission, scalable process, and the resource is recyclable. The proposed method is very promising to revolutionize the conventional one. Finally, I would like to thank the U.S. Army Research Laboratory for their financial support, and also thank you for your attention.